At this time, the best thing I would say is to jumpstart or kickstart the event with keynote speaker, and that is Anita Rao, and she has an excellent background. She has a 28 years of experience all put together. Put it, she has engineered at least 2 generations of chipsets or silicon or whatever SOC you call it. I'm no expert in that, but all I know is power is important, low power is important, and that is one of the main reasons she handled the Centrino code name, whatever it was, and that piece is what she has engineered to bring down the power, which is very important. And the other piece is obviously to ensure that low latency is maintained, and that is also Sandy Bridge. That's a well-known processor. Those are the 2 where she has contributed. And chipset is a year and years of efforts. You can go to any semiconductor technology player, that's a 15 billion for nothing, even to get to the level of just whatever physical layer. So physical, logical, there are many variations in that. All of that I want you to hear from the Anita's, what she did and how she did and how it has transforming the network along with the computing, because both have to come together. There is no way we are going to go just doing compute or just going network, and both means end to end we have to do, and that's the challenge. And I don't think many players in industry can even understand or grasp this subject. Forget about even deploying it. We have been struggling 3 years, and there is no end-to-edge computing. And if you want smart and connected communities, you need smartness. So that is another aspect of it. And then to bring them together to make sure that there is a product and there is a solution and it is economical. Too many, and latency, throughput, I can keep naming, it's never ending, but there is a compromise, there is a best of pros and cons, what we can do, and only a big industry player with a long ability can manage this. And with that, I welcome Anita Rao to take the floor and tell us about what she can do for us.
We appreciate it. Just as an introduction, I'm Anita Rao. I'm the VP and GM at Intel in the data center group. And I've been at Intel roughly about 29 years and have managed a variety of products ranging from starting out with chipset silicon development to a very large extent. Doing chipsets, I've worked on CPUs in my career, and then I spent more than a decade focused on building GPUs for Intel. Graphics processors, where we took our GPUs, basically we expanded from practically 0% market segment share, growing it to about 80% in the integrated space, not necessarily discrete GPUs like what NVIDIA has, but more in the integrated space. And then more recently, I became the GM of camera development, camera IPs that we integrated to our processors for the client segment. And about last year, I joined the data center, and what I managed there in the data center is the verticals for networking, connectivity, and storage. Okay, so any of the IPs or SoC designs, silicon designs that I used in the data center for the adjacent markets, that's what we work on, and that's what I manage at Intel today. So it's very, it's pertinent to the discussion that we want to have here on edge computing and the network automation. So I'm really happy and glad to be here, excited to talk at the summit. And the opportunity is very large. So I think we have to come together to collaborate so that we can innovate in the space and bring solutions through this network transformation. So moving into it, the other point I want to make is, if you just look at Intel, right, we are an IDM. What that means is we have process technology at the heart of everything that we do. So with Moore's law, you can pretty much double the density of transistors you can pack every 2 years. And we're able to do this. The economies of scale are so fantastic with that. You can bring in new architectural features, you can get power performance, you can increase performance ISO power. So, and that capability is what we've used in our CPU computes, in our GPU computes, and it's very pertinent to what we can do in the networking space as well. So, looking at, what we've done in terms of networking, no, we got legal to clear this.
This has gone through legal.
Intel legal has.
No, we're fine.
We're okay. The Intel legal department has approved. So on this, we've come a long way in networking technologies. So you go back into you look at the wireless technologies back in the 1980s. We had 2G, right, and that enabled mobile devices. Then we transitioned into 3G, and with 3G, basically we got, smartphones. And then when we transitioned into 4G, now we had the ability to transmit real-time video data. And here's a big change, a revolutionary change that's ahead of us with 5G. And 5G now is going to change the landscape where it will enable machine-to-machine interfaces and more intelligence in the system. So if you just look at it from the standpoint of the 5G revolution, this is going to be very large for us, cross-group at Intel, almost as large as, the time when we had Andy Grove and Gordon Moore, right? We had the infamous 180 turn when we shifted the company over from memories to microprocessors. This is almost as large as that. Okay, the ability to actually build solutions end-to-end from an endpoint device all the way to the cloud is something that we could actually bring together. Now, to meet the 5G's promise, it just does not require, increase in frequencies of wireless speeds, so to say, okay? You also need a very smart network to be put together. And I think there isn't one company on the planet who can do it all. Okay, and I think Intel is positioned very well to do this, and we are seeking out partners in the industry that we can work with so that, we can innovate, we can prototype, and then we can productize solutions that we can bring to market as we shape this, shape the industry around 5G enabling, bringing in edge computing, which I will, define as we go through further in the presentation here, and come up with solutions for the market. So what's really happening in the industry, right? We have data-driven services are becoming very pervasive, okay, and complex. And they require more compute and intelligence to be placed very close to the endpoint devices. Now, what do I mean by endpoint devices? These are, like IoT devices, or it could be IoT sensors, autonomous cars, smartphones, what have you. Okay, they're consuming a lot of data. As an example, if you just look on an average, a tablet consumes about 1.5 gigabytes per day. Okay, a drone which has video cameras installed on it with video could be consuming up to 18 terabytes per day. And an autonomous car would consume 4 terabytes per day. This is like mind-boggling in the amount of data that gets consumed. And for use cases like, virtual reality or augmented reality, it's quite phenomenal. It's about 3 terabytes per minute. So this explosion of data and latency requirements represents both an opportunity and a challenge for the service providers because they have to transmit, process, and secure this data. Legacy hardware, it lacks the flexibility and security and capability to innovate on these edge platform requirements. Okay, so what is of paramount importance for these services is the ability to deliver large amount or have a lot of bandwidth with ultra low latency. So that's going to be very, very critical as we come up with the solutions to support this level of data transmission. So let me try and explain what is it that we think we need to do now to solve this problem, right? So we have edge computing it's how do you actually define what exactly is edge computing? It's a terminology that's being thrown out there, right? So I'm going to take a stab at defining what edge computing means. Now, with the rapid growth of data, it's quite apparent that we need advanced intelligence very close to the endpoints. And these endpoints, like, whether it's smartphones or cars or whatever, IoT devices, they're producing and consuming data. Right, so to capture and accelerate this opportunity, the powerful data processing and analytic capabilities that exist in the heart of the data center, like in the cloud, right, those have to be strategically now placed closer to these endpoint devices. Okay, so by doing that, you're going to be able to reduce the latency of the data transmission to these endpoint devices and the way the data gets consumed. So by expanding these powerful capabilities of the data center outwards, the service and network providers can now deliver more powerful services, and they can reduce application latency by processing more data closer to the edge. And the other thing it can do is it can optimize TCO. Okay, so that's the total cost of ownership for the consumers. Now, in other words, what this means is the demand for 5G that it has will basically be the network's intelligence will now be more dispersed. And when it's dispersed, it means that it's going to be closer to the endpoints. Now, the foundation that Intel has put is network function virtualization. What that implies is, like in the, previously when we had certain appliances, like say a router could be utilized only maybe 10% of the time, right? And the rest of the time there was no way to use it because it just supported the routing function. What network function virtualization does is it virtualizes the hardware assets in the network so you can use it for other purposes. Now, the benefit of doing that is, you're increasing the utilization of your assets and your total cost of ownership can be reduced. So it's very, very significant that virtualization capabilities that traditionally, the IT providers used to have is now available pervasively in the network as well. Okay, and that's the foundation that we introduced with what we refer to as NFIC. Now, the other thing we can do is, when you look at 5G, there is ability for us to do a little more than that. 5G gives us tremendous amount of 10x improvement in bandwidth with 10x reduction in latency. So you can actually create network slices. What a slices is, you have a logical layer over your physical hardware assets, and it gives you a particular application that's running in that logical layer can be run horizontally through the network, from your endpoint where let's say it's your smartphone all the way to the cloud. If you have a certain application, 5G enables you to run that application in that horizontal slice. Okay, and that's referred to as network slicing. So at the end of the day, there's, the other thing that's of interest that we are seeing with edge computing is, if you look at, say, an Amazon has, their major, if you look at their cloud, they might have 7 or 8 data centers spread around the country. But if you look at a telco provider, let's take AT&T, they might have about 6 or 7 branch offices right here in the Bay Area. So when you're talking about edge and you want to place the compute very close to the users, they can actually monetize the fact that they have these little, they have more branch offices, more locally created. Okay, so there's an ability now that we are seeing both the comm service providers or the telco providers and the cloud service providers are both working towards figuring out how to get the edge computing to actually facilitate it and enable it in the industry. So if I were to summarize, so I said a lot of things here, but if you want to summarize what edge computing is, it's essentially you're taking a data center grade network and compute and storage, and you're placing it very close to the endpoint where you have these smart devices. And by doing that, you're letting the service provider, basically, it helps the service provider provide better services, with reduced TCO, with low latency, deliver data with security, and also comply with data locality that might be required. So that's really what edge computing brings. Okay, fundamentally it's moving the assets of the cloud closer to where the endpoints are. That's how we are defining what we mean by edge. Now the question is, where exactly is the edge? Okay, so the way, depending on, if you look at different customers, define the edge a little differently. Okay, so at a high level, the outermost processing layer of the network, where, or network reach, where you're making a transition from the network edge to your endpoint, is what we refer to the edge. And if you talk to, for example, a wireless communications provider, right? They would just use their physical, the physical part of the network, like a radio access network, for example, would be what they define the edge, because that's situated very close to the endpoint. Or if you look at an enterprise, right, like in the case of, let's say, Intel is an enterprise. They would have one big data center located in one city somewhere, okay, and it's servicing, the whole company. But then there would be smaller regional branch offices that are spread all over the planet. And it would be co-located with, to meet certain employee or business needs. In that case, that branch office or the regional office would be defined for enterprise as the edge. In the case of cloud, what you would see is the cloud essentially would have, if there's certain types of applications that the cloud is trying to provide, or a web tier based application, and they want to optimize on it, in that case, they might have certain computes that are closer to an endpoint, and that would be what they would define as the edge. So the only way this really works is you really need, for edge computing, it enables a very composable, flexible network. And the way you would do it is, let's say that you want to have a real-time broadcast of a football game, and you're running it on a bunch of virtualized servers. What would happen in that scenario is, let's say we are building a packet gateway, we would want to place that packet gateway in a stadium. And what that would facilitate is ability for us to broadcast, okay, that game to the users who are sitting in the stadium with very high quality and very low latency, because the packet gateway is in the stadium. Okay, whereas the same packet gateway, in the case of, let's say you were supplying, services to an IoT farming company, then latency really doesn't matter for the user. In that case, that packet gateway can sit in the cloud. So, it's essentially one use case is the same packet gateway application. In one case, it sits all the way on that side, okay, where it's sitting very close to, in the stadium, it sits right on the left-hand side of the picture. And in the right-hand side, you would have a scenario where you might be doing it for some type of an IoT farming company. So this is you can orchestrate with edge computing. What you can do is you can orchestrate the solution based on the services you want to provide, and still meet the SLA that is required, okay, by the use case. Okay, so now at the so garbled. Sorry about that, technology problems. So getting back to, so what is it that we're actually doing, right? So you have the network, you have the compute requirements, and there's work to be done here to find a solution that can work for many different usages to bring together the smart network and the improvements that are needed for edge computing. So very recently, end of last year, we had the introduction of the Xeon D2100 processor. Just to give you a feel for, its predecessor, And you don't have to literally take this as just Intel, but it's the type of features that we're bringing in here that's relevant to the type of technology we need to service what's required for edge computing and to improve the capabilities that you need in a network. So in this case, like the Xeon D processor that was built, it's really focused on building low power computing, and it meets many of the requirements that are needed for the edge. So the type of things that we're focused on is there is an Intel architecture, there's a mesh architecture that was built. Just adding in more cores into a processor of this nature is not a very straightforward thing to do. Okay, when you add in more cores, we had to go and architect a solution that had a fabric, which we call the mesh. And it's the way you're connecting up your cores, your I/O, your caches, your memory, so that you don't have any bottlenecks. And you're able to transmit data between cores and to memory and to the I/Os at very low latency and really optimized for power. So that's very critical when you're looking at, building a processor that sits in the edge, meeting both So fundamentally, we focused on many different parameters to improve performance. So on the networking performance, we looked at a big boost in the performance for network by 2.9x. Storage performance improved 2.8x relative to the prior generation. Okay. And a 1.6x improvement in compute. Now, largely this is done by two means. One is you're making a process technology transition sometimes, or it could mean that you're re-architecting or adding new critical features that enable some of the improvements here, or it could be a frequency boost, if you will, on the cores, on the CPU cores. The other thing is a focus on certain architectural features. As an example, we introduced what we refer to as the AVX instruction set. And AVX 512, basically you can run twice the number of cycles. Twice the number of speed of processing is twice that in the same number of cycles relative to its predecessor. Turbo frequency increased by about 11%, so we spread it up to about 3 gigahertz. Memory capacity increased to 512 gigabytes per second with 66 megahertz frequency on DDR. Quick assist technology, essentially this is one of the things we do look at is when you know that certain applications are hogging up CPU compute, you can find a way to accelerate that in hardware. When you accelerate it in hardware, you can free up some of the compute cores to go do other important processing stuff. So quick assist technology is basically an IP that I do in my organization, where you can do crypto, compression, encryption, decryption, all of that instead of using computes on the CPU cores, you could instead do it in fixed function hardware. Now we support about 100 gigabytes per second. This is almost a 2.5x improvement in performance relative to the prior generation. Now what's interesting for the edge is we're constantly looking for security, right, and sovereignty of the data. That's where that comes in play. The other thing is integrated into the same Xeon D processor, we also have all the Ethernet ports. We increased, actually we have 4x the number of ports compared to the prior generation. So there's 10 gigabyte Ethernet here integrated into the processor. So all these features and capabilities have been built on one chip. Okay, so the SoC, as we call it, system on a chip, it's been built with high level of flexibility, scalability, and high density, so that we can meet most of the requirements, whether it is for networking, for storage, and for the edge requirements, because form factor is very, very key here. On the edge, you want to be able to build something that's in a small form factor and it's low power, because you really want to optimize on space. So you can see that, the capabilities here actually facilitate us to support many use cases. Okay, so use cases, as you'd see in the industry, is, as an example, multi-access edge computing, or if you were to take the example of customer premise equipment or warm storage in the cloud. Different variants, the same solution of this SOC based on the vectors that we went and improved on can service many of these use cases and usages that are there in the industry. To give you an idea, right, there's, if you were to look at a multi-edge computing environment, here what you're looking for is data capacity. Okay, you want to grow the data capacity and you want very high performance. So we have about 29% network packet processing capability here in just having improved it. The other thing is, because we improved as I said, we improved fixed function hardware for cryptography and encryption, it freed up computing power. So now you can take advantage of anything that requires compute processing, now enables really the multi-access edge computing scenario. You just get more performance by doing that. And the second case is like a customer premise equipment. Here you're really looking for, for space constrained solutions, you're really concerned about the form factor. So you're looking for a low power solution where you can bring in something like a Xeon D processor to fit into the form factors that you need. And the other key things here is we have very good implementation flexibility with PCI Express and the gigabit Ethernet capabilities that have been integrated. And in the case of cloud-bound storage, we support with the Ethernet adapters, we have something called RDMA. Okay, and this enables us, this is very good for storage because you can DMA data to remote memory very quickly. And we do that by means of building that again in fixed function hardware. And the other things is we have the ability to reduce power. Now when you reduce power, you can fit more computes in the same rack space. Okay, or you can use the rack space to put more storage. So that's the type of idea where you can use one solution, one chip that meets the needs of edge computing. The other key thing is it's not just the Xeon D. What Intel has focused on is actually looking at the entire spectrum. We build cores. And in the cases like Xeon D, where you have integration of networking, IP, and features, if you are looking at the cloud, you can use what we refer to as the SP line of products. And what the SP line of products does is it gives you the best performance. It's highly scalable, but depending, you can actually carry it. So typically, if you were to look at the cloud, these are the type of devices you would see in the cloud. Okay, because they are very performant CPU cores. However, you can carry it to the edge, but it depends on how much operating space you have there and how much power envelope has been allocated for this use case. But if you're very constrained, if you're constrained for area, for operating space and for power, then you really want to go to something like a Xeon D. Because you have all the network functions integrated, it's focused on low power, and it's all about density and low power in the edge. So this is typically where you would land up using it. And if you want very custom solutions that are extremely low power, like if you want to integrate something into a smartphone or one of these devices, then you could use an Atom core, which is like the ARM cores. They're really small processors with computing capacity and capability. So, I mean, that's in a nutshell, how we are looking at the edge, okay, how we're looking at the networking capabilities that we want to innovate on and build. But it's a solution that can take us end to end, from the smart devices all the way to the cloud. So, thank you. Apologize for the many interruptions we had.
Before we leave her, I think I have one player here who probably can come forward. I think Gokhale, Professor Gokhale. He's from Osmania University, she's from Osmania University. At least he's 10 years senior to her and he has the luxury to give her only. My pleasure. So on behalf of the New Frontier Committee 2018, Anita Rao deserves to be the first one to receive this, and I give also Dr. Rao.
Thank you so much. Any questions for me? I'm sorry I forgot to ask. Okay, thank you.